Welcome to Everyday Mathematics. Here at Everyday Mathematics, we always see we do enjoy solving the harder problems, but above all, we also see and appreciate the beauty of the simpler problems. So today's problem comes from the MIT 2024 Integration Bee Quarterfinals number 2, and problem number 1 of the quarterfinals number 2 is what we'll be focusing on today, which is the limit as n tends to infinity, into brackets of the integral from x equals to 0 to x equals to 1 of the summation from k equals to 1 to n of kx to the power 4 over n to the power 5. So this is a very interesting problem. Now, before I jump into the solution to this problem, I'd like to thank our subscribers. Thank you so much for your support. Without your support, we wouldn't be here. But so we really don't take your support for granted. It's because of your support that we come here day in, day out to try and share with you our versions of the solution to these problems. To our new visitors, we would like to let you know that here at Everyday Mathematics, what we do is we go around and about and look for very interesting problems, and we come back and share with you some of the solutions that we think befit these problems. To our repeating visitors who haven't yet subscribed to our channel, we do really encourage you to consider subscribing to our channel. Your support will go a long way in giving us that extra visibility that we do need. Now, jumping onto the solution, so one thing I could do to try and simplify this problem is I'll want to decouple the k and x, and how I do that is the same as kx to the power 4 is the same as k to the power 4, x to the power 4. And since the summation only entails the k value here, we could now bring the k out and also the n, and then focus on integrating the x term. Then the next stage, I could bring out the n, since the n is a constant in here, so I'll bring it out. So we have 1 over n to the power 5, the summation from k equals to 1 to n of k to the power 4, integral of x from x equals to 0 to x equals to 1 of x to the power 4. Now, the integral there is simple. What we do get there is a fifth x to the power 5, and we have limits 0 and 1. So when you substitute that limit, or these limits, we are left with a fifth on the upper limit and 0 on the lower limit. So we have a fifth that we will pull out as a constant. So now we have 1 over 5 and the power 5 summation of k to the power 4. And this is where now things have become a little bit interesting. What is k to the power 4 summed from k equals to 1 to k equals to n? So we do that in order to obtain this. I'm sure it's something that when you have enough practice, you could easily memorize these formulas. But this is how one would go about deriving it. So we know that k to the power 5 when summed looks like this. And so when you go ahead from, as you can see, 2 is equivalent to 1 plus 1. 3 is equals to 2 plus 1. And then n is the same as n minus 1 plus 1, right? And then we can add n plus 1 minus n. So this essentially would cancel out, but let's keep that there. So this now allows us to say that now we do have 1 plus 1 to the power 5, sorry, plus the summation from k equals to 1 to n of k plus 1 to the power 5. And because this goes up to this point, and now we are left with this subtraction here. Okay. So when we go ahead, what we do is when we expand k plus 1 to the power 5, first of all, in order to include this index here, we could now shift this to k equals to 0. So from k equals to 0 to n, and that now involves this one. So we don't have this lingering 1 to the power 5. So expanding k plus 1 to the power 5 means that we have now k to the power 5 plus 5k to the power 4 plus 1 to plus 10 k to the power 3 plus 10k squared plus 5k plus 1. And these binomial constants can be derived from Pascal's triangle. So for 1 is 1, for 2 items is 1, 1, for x plus y squared, you have 1, 2, 1. To the power 3, we have 1, 3, 3, 1. Just by adding these two successive. So 1 plus 2 is 3, 2 plus 1 is 3, and so on. And then to the power 4, we have 1 plus 3 is 4. And then 3 plus 3 is 6. 3 plus 1 is 4. And then 1, 5, 10, 10, 5, 1. So using this Pascal's triangle, we are able to derive this constant here. So 1 for k to the power 5, 5 for k to the power 4, 10 for k to the power 3, 10 for k to the power 2, 5 for k, and 1 for it. Okay. So now when we expand this, we now see that these two terms are the same. So we can cancel this out, and now we are left with 0 on the left-hand side. Now we have 5 times k, summation of k to the power 4 plus 10, summation of k to the power 3 plus 10k, summation of k squared plus 5, summation of k plus summation of 1 minus the n plus 1 to the power 5. Okay, so we can reorganize by shifting these terms onto the left-hand side, and then reorganizing it so that we have the unknown on the left-hand side. Now we can also push this term up to here onto the right-hand side. And now we are left the summation of k to the power 4 can be obtained by dividing across that by 5. So we have now this n plus 1 to the power 5 divided by 5 minus we have this 10 divided by 5 is 2, so minus 2, summation of k to the power 3 from 0 to n. And then we have minus here, we apologize, minus and minus 2, since we have another 10 here, and then this 5 here divided by 5 is 1, and then since we have no constant here, we have a fifth. Okay, so we keep the minus here, the minus here, minus here. So we have now said, well, the summation of k to the power 3, we color code it as blue, summation of k squared, we color code it as green, summation of k, purple, and just this constant 1, we color coded it yellow. So then it's popular knowledge. We could also still derive it, but we don't want to spend a lot of time. The summation of k cubed from k equals to 0 to n is n squared times n plus 1 squared over 4. Summation of k squared is n plus 1 plus 2 n plus 1 over 6. And then summation of k from 0 to n is n times n plus 1 over 2. And summation of this constant 1 is obviously n. Substituting all that into now the equation for summation of k to the power 4 from k equals to 1, k equals 0 to n is going to be now n plus 1 over 5 minus 2. In place of summation of k to the power 3, we have n squared times n plus 1 squared over 4, and in place of k squared of n plus n times n plus 1 times n 2n plus 1 over 6, and so on and so on. So this can be simplified further into a simple equation that is summation of k to the power 4 is 6n to the power 5 plus 15n to the power 4 plus 10n cubed minus n over 30. Therefore, our limit as n tends to infinity of the integral from x equals to 0 to x equals to 1 of the summation of from k equals to 1 to n of kx to the power 4 over n to the power 5 is equals to the limit as n tends to infinity of 1 over 5n to the power 5 times the summation of from k equals to 1 to n of k to the power 4. Now we know what this sum is. We just bring this entire expression in place of that summation. And so we put in bracket 6n to the power 5 plus 15n to the power 4 plus 10n to the power 3 minus n over 30. And then we can separate those individual items in the numerator so that we do have 6n to the power 5 over 30, which is n to the power 5 over 5. And then 15n to the power 4 over 30 is n to the power 4 over 2. And then 10n cubed over 30 is n cubed over 3. And then minus n over 30, which is minus n over 30. So as we go further, we see that this n to the power 5 and n to the power 5 cancel. So we have 1 over 5 times 5, which is 1 over 25. And then this divided by this, we have 1 over 10 to the power n. 1 over 10n. And then this is plus 1 over 15n squared minus 1 over 5 times 30 is 150. And then this n and this cancel, we have n to the power 4. So as n tends to infinity, we see that this entire expression goes to 0. This expression goes to 0. And this expression goes to 0. Because why? Because we have this n in the denominator, and as they tend to infinity, the entire fraction tends to 0. So we're left with now a 1 over 25 plus 0 minus 0. So our answer is 1 over 25. So the bigger challenge here was in finding what the summation of k to the power 4 from k equals to 1, or k equals to 0 to when k equals to n. So that expression just, I think, was a challenge. Maybe there are other ways to go around that. If you have any ideas about it, please share with us. We're here to learn, we're here to share, we're here to grow. So it was an absolute pleasure going through this problem with you. Until next time, adios.